Welcome. In today's video, we are going to be looking at how to derive the moment generating function of the Bernoulli distribution. So to begin with, let us first recall the probability mass function of the Bernoulli distribution. So remember, if x is distributed Bernoulli with parameter p, in other words, your probability of success is characterized by the variable p, or the parameter, sorry, I should say p. Then the probability mass function is given by this result here. P of x is p1 minus p, p to the x, and 1 minus p to the 1 minus x, when x is an element of 0 or 1. And sometimes that can be written in a more common form, and that is equal to p when x is equal to 1, and 1 minus p when x is equal to 0. So of course, if you were to plug in those values of x and those values of x equals 1 and x equals 0, you'd end up with this binary result. However, for the purposes of what we're going to be doing today, I'm going to be sticking with this expression here, only because it's a bit easier to use. So, the moment generating function, or I'll say the MGF of x, is actually given by, if we recall the definition, we usually write it as mx of t, and by definition this is equal to the expected value of e to the tx. Now, in the context of a discrete random variable, which is what we're dealing with here, a Bernoulli distribution, we're going to rewrite this as the sum, not the integral, but rather the sum across all x of e to the tx multiplied by px of x. Now, here's where that Bernoulli distribution comes handy, or that comes in handy. We're now going to first, in the summation sign, we're going to consider all the possible values of x. Well, we know from we actually know from our expression up here, x can only take values between 0 and, or not even between, just simply 0 and 1. So in the first part of the summation, I'm going to write x is equal to 0 and then to 1, because those are the only two expressions. Now, e to the tx, there's not much more we can do to e to the tx right now. So instead, I'm just going to rewrite it as e to the tx. And then, of course, for expression px of x, that we're going to use this expression up the top, because I think that is more conducive, or it's at least easier to substitute than, say, for example, this binary sort of, what do we call it, a piecewise sort of function. So instead we're going to write p to the x 1 minus p to the 1 minus x, which is why I had that expression there in the first place. And now simply we can substitute in our two values x equals 0 and x equals 1. So this becomes e to the t times 0. Then we've got p to the 0 here, and then 1 minus p to the 1 minus 0 for the first instance, and then that's for x equals 0. And then again, we're going to substitute x equals 1 into this expression at the top here, so we're going to get e to the t times 1, p to the 1, and then 1 minus p to the 1 minus 1 here. So far, so good. We're going to apply a few more simplifications. Apologies there. So e to the t times 0 that's just simply equal to 1, because anything to the power of 0 is 1. P to the 0 is just simply, again, times 1, times here what we've got is 1 minus p to the power of 1 minus 0, and anything to the power of 1 is just itself. So now what we can write is 1 minus p, and we can put that in brackets. Now simplifying the next section, you've got e to the t times 1. Well, that's simply just e to the t. You got p to the 1 as well here. That just becomes p. And I'll put a multiplication sign. And then here you've got the power is 0, and we know that anything to the power of 0 is 1. So then this expression altogether here becomes 1. And so in a more simplified form, we have 1 minus p plus p e to the t in its simplest form. And this is in fact the moment generating function for the Bernoulli distribution, sorry. So now what we're going to be interested in is we're going to use this expression to actually calculate the moments. In fact, we're going to calculate the first moment, the second moment, and also the variance, specifically using this definition. So in order to do that, let me just rewrite our expression here. Mx of t was equal to 1 minus p plus, I believe it was p e to the t. So before I do any of those calculations, and remember the first moment as an aside that I'm just going to put here, again, remember that the first moment of x is given by the derivative evaluated at 0, and the second moment of x is given by the moment at the second moment at 0. So that's where we're going to land. But so first what we're going to do is we're going to calculate these two aspects here. We're going to calculate those two functions. So we need to calculate mx of t prime, which, if you recall, is d on dt of mx of t, all in brackets, which we're going to write as d on dt of 1 minus p plus p e to the t. And this is sort of a fairly simple expression to calculate, because if you have a look here, we have our expression in this form. Sorry, we have nothing dependent on t here, so they're effectively constants. They become 0 when differentiated. And then over here we have p e to the t, and we know that the derivative of e to the t is just itself. So eventually this just becomes p e to the t. Quite simple, in fact. Then, equally, we're going to calculate the second derivative of this function with respect to t. So the second derivative with respect to t is actually the derivative of the second derivative is the derivative of the first derivative by definition of what derivatives are. We've already calculated our expression for m prime, or the first derivative with respect to t of the moment generating function. So then we're just going to plug in that result here, and that gives us p e to the t, which is pretty straightforward. And again, we know what this expression comes out to be. It just becomes p to the t because the derivative of the exponential is itself. So now we can go back to these two definitions here. And again, we can write e to the power of x is equal to mx prime at 0, which, if we have a look here, remember we have mx prime, so that was a bit of a funny little movement here, but let me just clean that up for a second. Mx of t was equal to this, and mx prime of t is equal to this. So, going back here, we have mx prime of t. We're going to substitute that in here, the expression, and we're going to evaluate at p is equal to 0. So this is, sorry, t is equal to 0. So pe of t at when t is equal to 0, which is simply equal to pe to the 0, which is equal to p, because anything to the power of 0 is 1. So you get p times 1 gives you p. Then we're going to calculate the second moment. So if we have a look, x squared is equal to mx double prime at 0, which again, we know what mx double prime at 0 is. It's me to the t, pe to the t. We're going to also evaluate that at 0, and we end up with the same result, p. And so after we've calculated the first, second moment, and finally we're going to calculate the variance with respect to x. And this is the expected value of x squared minus the expected value of x all squared. We're going to substitute in our values. We know that the first value is p from our workings above. We know that the second value is p, but we have to square it, so we've got the p squared. And then we're going to use a commonly formed expression of the variance, and we're actually going to factorize out p, so you get 1 minus p times 1 minus p. And there we can verify here, we already know what these are. We can verify, in fact, yes, that the expected value of x is p. We're aware of that. We also know that the variance of x is also given by this expression here. So everything seems to be working out. Thank you for listening to this video. Hope to see you in the next one.